Welcome everyone for this webinar on carbon-14 for climate issues for dating and climate. So the radiocarbon is a special case for the metrology community. On the one hand, and due to its radioactive nature, it's a subject for ionizing radiation metrology. On the other hand, it's at the center of applications aimed at quantifying its isotopic abundance in certain materials or gases. In this respect, it naturally concerns the metrology of amounts of substance classified here in chemistry metrology. Today's CCRI webinar will provide an opportunity for both CCRI and CCQM members to better understand the issues related to radiocarbon measurement. To shed light on this subject today, we are pleased to welcome three eminent speakers. Dr. Adam Fleisher from NIST, who will speak about an innovative technique called infrared spectroscopy of radiocarbon. Then, Dr. Jocelyn Turnbull from NOAA will speak about the radiocarbon as a tracer for the source and fate of fossil fuel carbon dioxide emissions. Finally, Dr. Emmanuelle Delqué-Količ from CNRS will speak about radiocarbon dating for archaeology and cultural heritage. These presentations will allow us to discover different aspects of radiocarbon. The first presentation will focus on the metrological aspect, while the other two will focus on two essential applications of radiocarbon: the tracing of greenhouse gases and dating. I'd like now to open a short parenthesis to promote an important upcoming event related to today's discussions. Indeed, today's presentation will also be very useful to our community as an introduction to the upcoming workshop on metrology for climate action. This event will take place from the 26th to the 30th of September. The aims of this workshop are to present progress and identify requirements for further development of advanced measurements, standards, reference data, comparisons, calibration, and methodological techniques to support the physical science basis and for an adaptation to climate change, as well as efforts to mitigate greenhouse gas emissions. The workshop will be divided into two main themes. Themes number one is metrology in support of the physical science basis and climate change and climate observations. Theme number two is metrology as an integral component of operational systems to estimate greenhouse gas emissions based on accurate measurements and analysis. Please follow this link for more details about the content of the workshop. It will be copied also in the chat. Please also note that the submission of abstract for the workshop is for today. So sorry for the very short notice. However, you can still submit abstracts in the coming weeks. In the coming week, they still be considered. Abstract will be analyzed against a number of expected criteria. First, papers and posters submitted to the open call should include as many of the following elements as possible or appropriate. Number one, introduction to progress or lack of progress so far. Number two, indication of what is needed to improve the information content in environmental measurements or models. Number three, proposals of new or existing tools not currently in use for improving information content. Number four, description of potential means to achieve that improvement. And number five, opportunities for collaboration between communities to achieve this improvement. The main message here is that we are looking for recommendations of future required work and not just completed activities. If you have a point of view on this subject, it's a great opportunity to share it with us. All posters and presentation will be pre-recorded and made available before the week of the workshop. This will allow us to optimize the exchanges we will have during the interactive sessions and meetings. Indeed, thanks to the GatherTown platform, a virtual conference experience will be offered to you. During the workshop week, the objective will be to develop recommendations on methodology to address the issue of climate change. This will be based on the exchange during the week, which we hope will be fruitful. I am closing this aside to return to today's webinar and now hand over to Dr. Adam Fleisher for his presentation.
All right, well, thank you very much for the introduction, and thank you to the CCRI for the invitation. I'm representing our group at the National Institute of Standards and Technology in Gaithersburg, Maryland, in the US. And as Romain mentioned, the title of the talk is Towards Accurate Infrared Spectroscopy of Radiocarbon. And I've added an additional word to be a little more specific. We're going to talk about radiocarbon dioxide. And this will be a talk that introduces emerging techniques using infrared lasers, optical cavities, and well-measured gas samples to try to determine amount of substance for C14, CO2 in a neat sample. Broadly speaking, what our group works on at NIST is the measurement of spectral reference data in order to accurately model molecular absorption in atmospheres. That's one key thrust of our group. The spectral reference data is then applied to the measurement of top-down greenhouse gas inventories over various scales. So this is a background and a strength that we have. And we're also interested in applying this strength in our ability to measure spectral reference data for molecules to applications beyond Earth's atmosphere. And in both of these applications, isotopic composition, stable and radioactive isotopes, particularly for carbon, as we're focused on here today, help researchers disentangle and understand sources and sinks of molecules like greenhouse gases. How we routinely do this in the laboratory is using a technique called cavity ring down spectroscopy. This is a technique depicted here. Where we have a gas sample. In this case, maybe we've taken a flask of air and maybe purified the CO2 or extracted the CO2 out of that flask of air. And then we might introduce that sample in the laboratory into an optical cavity. This is a Fabry-Perot resonator constructed of two highly reflective mirrors. And we'll introduce a gas sample in between those two mirrors and study how the light interacts with molecules in that sample as a function of the frequency of the laser. And then at the outcome, we'll measure an absorption spectrum. From a metrology perspective, what's important to us here at NIST is that we can introduce samples with either a known or an unknown mole fraction of absorber. The technique of cavity ring down spectroscopy allows us to measure absorption as a function of optical frequency, which we can measure very well. We can measure temperature and pressure of our sample quite well, and with high traceability to the SI. And the outcome is the spectral reference data with high traceability to the SI. Of course, there's a connection between the mole fraction and the spectral reference data that we measure. If we wish to report spectral reference data, then we're using a sample with a known mole fraction of absorbers. However, if we have that spectral reference data and we've studied it well, then we can use that to accurately retrieve mole fractions. And it's this concept that we'll talk about today. where we're trying to accurately retrieve mole fractions and maintain traceability within the concept of the SI, particularly the new SI. So the applications that are important today are both stable and radioactive isotopes and the study of isotopic composition, particularly for CO2 and other greenhouse gases that we've looked at in our laboratories, including N2O. But there are numerous applications, and you'll hear a great deal more about them in the next two talks. Our contribution to radiocarbon detection was first reported several years ago in a paper from 2017, where we built a cavity ring down instrument to differentiate between natural abundances of radiocarbon, so about 1.2 parts per trillion in a natural sample, differentiate between those biogenic CO2 or natural CO2, current levels of CO2, with petrogenic samples or samples that were entirely depleted of the radiocarbon isotope. So you can see here, these spectral plots have a y-axis, which is related to the amount of absorption, and an x-axis, which is the frequency of our laser that we're tuning across the absorption feature. And you can see the bump on the left-hand side here, on the left-hand side plot, is our absorption feature for radiocarbon, and that bump is absent in the petrogenic sample of CO2. So in our first instrument, in our first experiment, what we were able to do is clearly differentiate between CO2 from natural sources and CO2 from petrogenic sources. And this is already a good step forward in trying to address carbon use and carbon source for climate and environmental applications. We're not the only game in town, and the use of optical instruments to measure and detect radiocarbon was sort of jump-started, I should say, in the year 2011, when the team at INO and CNR in Italy demonstrated saturated absorption cavity ring down spectroscopy. So that really jump-started this field for detecting radiocarbon with laser-based instruments at natural abundance levels, or fraction modern of about 1. So the INO CNR group has really been leading in terms of sensitivity, demonstrating parts per quadrillion levels of sensitivity for precision measurements of radiocarbon. And these are only two references of several of the papers that they have. There's also an outstanding group at the VTT in Finland, which has been pushing cavity ring down spectroscopy of enriched samples of CO2 that are enriched in radiocarbon. One of the applications that they target is fugitive emissions from nuclear power plants. And they've done an excellent job of building instruments that have an opportunity to even go outside of the lab to study maybe ppb levels of radiocarbon, potentially outside the laboratory. And then there's a third group at Lawrence Livermore National Lab, which has demonstrated both cavity ring down spectroscopy and a new nonlinear technique, a double resonance pump probe technique, which show great promise for detecting radiocarbon. So there are several groups around the world that are pushing on sensitivity and laser instrument design, including us. One of the things that we all share in leveraging cavity enhanced spectroscopy are these advantages. We get a long interaction path length between our laser and our sample of interest, our CO2 sample. So we have kilometers of absorption path length in a compact tabletop footprint. Get a very stable frequency axis, which is important for performing the spectroscopy accurately. Importantly, we're interrogating a sort of spatially confined region of molecules. So we know which molecules we're studying, and that's a sort of well-confined experiment. And we have high spectral resolution, high quality factors, high finesse, which are important for the instrument development side. Essentially means that we have a high degree of certainty that we're interrogating the correct molecule and the correct absorption feature that lends itself to selectivity of the optical spectroscopy, infrared spectroscopy techniques. And again, the technique we're using is this cavity ring down approach. So we are pumping one transmission mode of the Fabry-Perot resonator. So here you see a transmission spectrum of one of our optical cavities, where we have these discrete frequencies, which are the frequencies at which we can sample the molecules in our cavity. So we can pump one of these modes, then we'll end up with a constant bit of cavity transmission. And then in all the experiments I'll talk about today, we'll shut off our laser light and we'll observe a passive decay. And the decay rate is going to be related to the amount of molecules inside our cavity as a function of frequency. On our optical table, it looks something kind of like this. So we'll have a laser and then a switch for shutting off that laser. We'll probably roughly monitor its frequency with a wavelength meter or something similar. That light will be spatially mode matched into our optical cavity. For radiocarbon, this is a cold optical cavity. So we're performing these experiments at about 200 Kelvin and at low pressure, at around 2 kilopascals or 10 to 20 torr in that region. The light inside of our optical cavity will decay once shut off. We'll detect that decay on our photodetector. There will probably be some control systems to maintain resonance between the laser and the cavity. And then our outcome will be this absorption spectrum as a function of frequency. So we're measuring decay rate. The decay rate is related to the losses in the cavity. The losses will increase as we scan our laser across a molecular absorption feature. And importantly, we can tell the number density of molecules in our sample based on the absorption alpha if we know the absorption line strength, which is S, and the line shape parameters. So S and G together are referred to as the absorption cross-section for the molecules. So that's where we need our reference data if we want to accurately report a number density from our experiments. What do we do in the laboratory to improve confidence and reduce uncertainty in the spectral reference data? Well, we focus on measuring these absorption cross-sections for the major isotopic log of CO2 and soon for the stable C13 CO2. And we compare those measurements of absorption cross-section, which we make in the laboratory, to high levels of ab initio theory and quantum chemistry theory. So what you see on the right-hand side here is a plot of how our measurements of absorption cross-sections for a certain CO2 transition agree with theory. So this is a deviation from theory for, on the y-axis, several vibrational bands at around 1.6 microns and 2 micron wavelengths in the infrared. And you'll see that on average, we agree reasonably well. There's still some scatter about the measurement accuracy error bars. So our measurement accuracy is sub 0.1% in most cases. Our agreement with theory is sort of sub 0.5%. So if you're used to thinking in parts per thousand, we're at that level of accuracy and intercomparability with theory. And that's going to be important for how well we think we can accurately report any isotopic composition. There are a number of things in the laboratory from a metrology perspective that we have to care a great deal about. And I'll just breeze through a few of them because they'll be quite familiar to many people in this community. And you can also check out the references to learn a little more. But when it comes to cavity ring down, we have to be quite careful about how our signals are digitized and make sure that we're not distorting the optical decays. One of the great advantages of cavity ring down spectroscopy is that the passive decay from the cavity is purely exponential. At least ideally it should be. So any deviation from exponential behavior due to nonlinearity in your detection system or chain has to be watched out for. And that's something that we showed that we could do quite well in 2019. Other potential driving sources of uncertainty for any budget where we're trying to report a number density. Well, we have to know the sample temperature and pressure quite well. And thankfully at NIST, we have great access to primary and secondary temperature standards, which can help us accurately calibrate any thermometers that we have connected to our sample. And the same thing goes for pressure. We have direct calibration for our pressure gauges to secondary NIST pressure standards and then also primary NIST pressure standards. So in terms of our relative uncertainty, temperature and pressure, thankfully, aren't anywhere close to limiting what we can report for number densities, isotopic composition, and spectral reference data. One example that I'll go through briefly here, which might be of interest to this community who's discussing how to accurately quantify isotopic composition, particularly radiocarbon, is the test case that we've recently reported on the accurate measurement of the stable isotope C13. And in this case, we're accurately measuring the C13-C12 ratio in samples of CO2, in this case, CO2 in air, so around 400 parts per million of CO2. And the delta 13 ratio is a pretty well-known ratio in the isotopic measurement community, and the scale is defined by the virtual reference material Vienna PDB with some traceability back to the original PDB sample. So what we did is led by Hongming Yi when he was in the laboratory, was we built a 2-color cavity ring down instrument so we could measure simultaneously in the same mode volume, both C13 and C12. And I think important for this community, what we were able to show is that we could accurately measure with our infrared instrument the absolute C13, C12 ratio in the virtual reference material. So the question we're trying to ask and push ourselves is, instead of having physical artifacts define these isotopic composition scales, can we instead use accurate infrared spectroscopy, along with other accurate methods from colleagues, to value assign the artifacts with traceability to the SI? And can we do that with a high enough precision that it's actually a value for practitioners in the field who are making measurements relative to these reference materials? So those are 2 different challenges, and we're focused on sort of the metrology side and allowing others to really push on the precision. We're focused on the accuracy side. But on the right-hand side, what you'll see is on the y-axis is just sort of a chronology of measurements of the absolute C13, C12 ratio in Vienna PDB. On the bottom is that ratio in percent. And the original measurement by Craig, made in the late 1950s on the original PDB sample, is still largely used by the community as the chosen sort of absolute reference value. IUPAC defined a value in 1990, which is somewhere over here. Others have measured more recently slightly different values. The Avogadro project, which is probably pretty well known in the metrology community, measured an extremely high accuracy value. A lot of these were done with mass spectrometry, different varieties of it. Here's our cavity ring down measurement, the one with the biggest error bars, but we're on the chart. And very recently, someone has made a proton NMR measurement to try to determine this isotope ratio. And the point is, we're all in pretty good agreement. So this is a good example of having different measurement methods try to tackle the absolute isotope ratio in a reference material with this idea of making the reference materials traceable to the SI. So that's also a story that's probably relevant for radiocarbon. So back to radiocarbon, right? We're trying to at NIST create this measurement technology to enable essentially the honest brokering of emerging carbon markets. That's an application where we think we can add some tabletop instruments that would be of high value, and also push on the SI traceability of measuring radiocarbon and other isotopes with infrared spectroscopy. So the first application that we were able to test, again, is this biofuel application, where we're sort of making a binary measurement, right? We're seeing if the radiocarbon is fraction modern, close to 1, or not there at all, right? And we could do that with about 10% fraction modern uncertainty. So modest, but again, able to see and detect this fraction modern of 1, which was a first for the linear absorption cavity ring down. So the first without using a nonlinear technique. Again, here are the examples of the spectra. These are the same spectra that I showed earlier. Again, noting here that we were able to do this in a measurement time under 1 hour. So the measurement time for many of the experiments that folks have reported is anywhere from minutes to several hours. So there's potential for the infrared techniques to quickly give answers to some of these lower precision applications, and in that sense be complementary to the highest precision methods that I'm sure you'll hear about in great detail in the next 2 talks. briefly, where we're going next, in my last minute here, I'll close up. Where we're going next is we're building a next generation instrument. This is going to give us improved temperature stability, allow us to more confidently and more reproducibly measure spectra. And it's important to note that these optical instruments are usually dealing with pretty reasonable amounts of carbon. So we're talking about milligrams of carbon, in our case, about 10 milligrams of carbon required to make one measurement with these cavity ring down instruments. But we think we can improve our uncertainty budget by about an order of magnitude if we do this next generation instrument quite well. So we're hoping to get down to the 1% sort of level of fraction modern. In order to do that, we've made a lot of advances in the related laser and optical technology required to do this. And some of those references are here, and I'm happy to share them with others. So I'm just going to close here by saying, thank you to all the people that have worked with us here at NIST, all the collaborators, all the folks who work on ab initio and quantum chemistry theory, as well as our collaborators on archiving spectral reference data. So thanks very much for the invitation, and look forward to hearing the next two talks as well. Thank you.
Thank you very much for having me. And I apologize, I have some troubles with my camera, so you won't be able to see me, but hopefully be able to hear me and see my slides. So I'm going to talk about radiocarbon in the atmosphere. So out there in the environment, things are a little messier than what we saw from Adam in the lab, but I hope it'll give you an idea of some of the really neat things that we can do with radiocarbon measurements. So what I'll do is, first of all, talk a little bit about an introduction to the carbon cycle and radiocarbon, and then I'm going to give two examples of how we can use radiocarbon to trace fossil fuel CO2 emissions out there in the world. So many of you will be familiar with the graph on the left. This is the Coulon curve that shows the rise in CO2 in the atmosphere since the 1950s. And that is, of course, due to burning of fossil fuels primarily, and that's the graph on the right showing what we think we know about emissions of fossil fuels over time. What is less well known is that only about half of the CO2 that we produce from burning of fossil fuels stays in the atmosphere. So the graph there on the left, the blue line is the same one I just showed, the Coulon curve that shows CO2 increasing in the atmosphere. And the pink line is what CO2 would be doing in the atmosphere if all of that CO2 that we're producing from burning fossil fuels stayed in the atmosphere. And so you see that big difference. And that big difference is because the land biosphere and the oceans are doing us a really big favor by absorbing about half of our emissions. And we put that into the carbon cycle, and this is a simple schematic of the modern carbon cycle. So we have CO2 in the atmosphere, which is currently a little bit over 400 ppm, close to about 415 ppm in the Northern Hemisphere right now. And we are burning fossil fuels, shown there on the right, injecting about 10 gigatons of carbon into the atmosphere every year. But then we have these big exchange processes with the ocean and the land. So with the land, we have photosynthesis, where plants absorb CO2 from the air and use it to grow. And then we have respiration that returns CO2 to the air. So respiration comes from plants themselves, from soils, and from animals. And there's a similar exchange process going on in the ocean as well. Now, those exchanges between the land biosphere and the atmosphere and the oceans in the atmosphere actually have much larger fluxes in each direction than the amount of fossil fuels we're putting into the atmosphere. But on average over the year, those natural fluxes approximately balance out. Since we've been adding fossil fuels to the atmosphere, those natural processes are not quite balancing out. They're taking up a little bit more than they're releasing each year. And so one of the consequences of this is that if you want to understand what our emissions are, it can be quite difficult if you just go out and measure CO2 concentrations in the atmosphere, because you're seeing all of these processes together rather than being able to isolate the fossil fuel emissions. So this is where radiocarbon comes in. So as Adam already talked about, radiocarbon is produced naturally in the atmosphere. It's produced by interaction of cosmic rays in the upper atmosphere. And that radiocarbon that's produced oxidizes quite quickly to form radiocarbon CO2, 14CO2. And then that 14CO2 moves throughout the carbon cycle along with the regular carbon-12 and carbon-13 CO2. And anything that's exchanging with the atmosphere routinely will keep getting its radiocarbon renewed from the atmospheric exchange. But anything that is out of contact with the atmosphere will start to lose radiocarbon through radioactive decay. And so this becomes really useful when you're looking at fossil fuels, because of course they've been out of contact with the atmosphere for millions of years, so they have no radiocarbon left at all. And so we can exploit that. So let's have a look at what radiocarbon looks like in the atmosphere. This is the record of radiocarbon in CO2 in the atmosphere from right here in Wellington, where I live, from 1954 through to the present. And this, just for a little bit of history, this record is the longest direct atmospheric trace gas record in the world, starting in 1954. So what you see here is we're using this weird isotopic delta notation, in which 0 means that the sample has the same isotopic content as our standard, which in the case of radiocarbon, the standard is meant to represent something from the 1950s. So you see the early part of this record, we have a value of about 0. And then the big spike, this is what we call the bomb spike. This is where atmospheric nuclear weapons testing produced radiocarbon along with a bunch of other radionuclides in the atmosphere, mostly in the Northern Hemisphere in the 1960s. And that caused a near doubling of the amount of radiocarbon in the atmosphere, which on the delta scale, a doubling is 1,000 per mil. And so you see this very large increase in the 60s. If you looked very closely, you might notice that the peak here is in early 1965, which is a little later than when the atmospheric bomb tests happened. And this it's because this record is from the Southern Hemisphere, and it takes a little over a year for air to exchange from the Northern Hemisphere, where all the bombs produce the radionuclides, to the Southern Hemisphere. So we get that little offset. Then you see this sharp decline in radiocarbon again after the bomb spike. That's not radioactive decay. There's a little bit of radioactive decay there, but that happens much more slowly. What we're actually seeing is that newly created radiocarbon, CO2, moving into the oceans and the land biosphere, trying to find an equilibrium in terms of isotopic content. And then when we get out into the more recent period, we see an ongoing decline in this delta 14C, and that's really primarily driven by the continued emission of radiocarbon-free fossil fuel CO2 that keeps diluting the amount of radiocarbon in the atmosphere. So we can put this together of everything that we think we know about radiocarbon and put this into a radiocarbon cycle that looks something like the carbon cycle. We still have the exchange with the oceans and the biosphere and the emission of fossil fuel CO2 into the atmosphere. But what's changed is that the oceans and the biosphere are continually exchanging their carbon with the atmosphere. So the amount of radiocarbon, the radiocarbon content in those reservoirs is quite similar to the atmosphere. Whereas fossil fuels that are millions of years old have no radiocarbon left in them at all. So now we have this very big lever from the fossil fuel CO2 that allows us to separate that from the other exchange processes. With radiocarbon, we also have to consider that natural cosmogenic production of radiocarbon in the upper atmosphere. And we also have to consider not only the nuclear bombs from the 1960s, but there's an ongoing small source of radiocarbon from the nuclear power industry, from both reactors and reprocessing and so forth. But nonetheless, we can exploit this fossil fuel CO2 having no radiocarbon. We can calculate the amount of fossil fuel CO2 in an atmospheric sample from observations of radiocarbon in the atmosphere, as shown in the equation, which I'm not going to attempt to explain. And we can see what this looks like in the world. So what I'm showing here is a global atmospheric transport model in which we've put in everything that we think we know about radiocarbon. The map on the left is the model prediction of fossil fuel CO2 concentrations at the Earth's surface. So we've said where do we think all the emissions are, and we've emitted them into the atmosphere, and then they've been transported. The graph on the right is taking all of those different sources and sinks of radiocarbon that I showed in the previous slide and putting them all into a model and predicting what this radiocarbon delta 14C looks like at the surface of the Earth. Now I've flipped the scale, so on the left for fossil CO2, red is a high value, and on the right for radiocarbon, red is a low value. And you see that these two maps look very, very similar. You see obviously all the big industrialized areas around the world mapping there. So even though there's a lot of different things going on with radiocarbon, emissions of fossil fuel CO2 are very much the dominant driver of the spatial variability in radiocarbon that we see in the atmosphere. And so again, by making these measurements, we can infer fossil CO2 mole fractions or concentrations from radiocarbon. Now you will notice that in the southern hemisphere, the match between these two pictures is not as good, and that's because in the Southern Ocean, upwelling of deep waters that are very old and have been out of contact with the atmosphere for thousands of years, actually, when they exchange carbon with the atmosphere, they're also somewhat depleted in radiocarbon. And so that's another thing that we can use radiocarbon for, is to try to understand that exchange of carbon in the Southern Ocean, which is another crucial aspect of what's happening in the carbon cycle. But I won't have time to talk about that further today. I'll focus on the fossil fuel component. So the first example that I wanted to show you is from the long-running Indianapolis Flux experiment, or INFLUX. So this is one of the first urban-scale greenhouse gas observational networks that was developed, and it's been running since 2010. And it's a consortium of a number of different research groups, mostly in the US, of course. And we're making a bunch of different measurements to try to understand greenhouse gases from the city. So I'll just show some small part of that today. So the first one is using aircraft measurements to do what we call a mass balance. So you can imagine you have a city, you have the wind flowing over that city, and as the wind flows over that city, the emissions from the city get into the air masses and get transported downwind in a plume. And so you can fly an aircraft downwind of the city, and you can map out where that plume is downwind of the city. If you also measured the wind speed and the wind direction, then you can put that together, and you can imagine that you're measuring a hose pipe coming out of the city, and you can write an equation to calculate fairly simply what the flux of your gas is coming out of the city. And this works reasonably well in good conditions. And so what's shown here is a series of 9 flights in 2014, in this case, over Indianapolis in the winter time. And we measured the flux of CO2, total CO2, and of CO, carbon monoxide, which is shown in the blue there on the graph. And we did this for each of 9 flights, and we're able to calculate average emission rates for these 2 gases for this period. So what is the flux? But of course, neither of these is fossil CO2. So what we did is we also measured radiocarbon. Now, Adam showed the really exciting new prospects of laser spectroscopy for measuring radiocarbon, which will, we hope, eventually mean that you can measure radiocarbon continuously at really high resolution. But for the moment, we are still using techniques where we have to bring samples back to the lab and analyze them using accelerator mass spectrometry. And so that means that we're limited in the number of radiocarbon measurements that we can make. But nonetheless, we've been fortunate, particularly in Indianapolis, to be able to collect a lot of flasks over the years. And I'm showing that data here. These are flasks collected on towers around Indianapolis. So the radiocarbon on the left at the top, you see the time series for about 4 years of data. And so you see this long-term decline, which is that continued addition of radiocarbon-free fossil CO2 into the atmosphere. And then the colored points are the sites that are downwind of the city, and you see lower values downwind of the city where we're seeing polluted air that has more fossil fuel CO2 added into it, decreasing radiocarbon even further. We can use the equation shown below to calculate fossil CO2 shown in the bottom left panel. So that's the fossil CO2 added by the city. And then for CO2 in the middle, you see here a gradual increase over time from the addition of fossil fuel CO2. You see this huge seasonal cycle, that's the biosphere breathing. And then again, the colored points are the deviations from that seasonal cycle. And by comparing the locations downwind of the city with the gray points, which are site upwind of the city, we can calculate an enhancement or excess shown in the bottom panel. And we can do the same thing for carbon monoxide shown on the right. And then we can look at these and compare these gases to each other, doing correlations. So I'm showing two correlations here. The one on the left is fossil CO2 on the x-axis, and the enhancement or excess of CO2 itself on the y-axis. And the black line is the one-to-one line. So if all of the CO2 that was being emitted over the city was from fossil CO2, all the points would fall on the one-to-one line. Now in the summer in grey, you see all sorts of scatter, and that's because there's lots of land biosphere stuff going on with photosynthesis and respiration. But even in the winter, you see that the correlation is not one-to-one, it's about 1.1 to 1. So there's a little bit more CO2 being emitted than just from fossil fuels. And that tells us there's a bit of a source from biospheric things such as people breathing, biofuels, and also respiration from plants. And then on the right, this relationship between fossil CO2 on the x-axis and carbon monoxide on the y-axis is really useful because carbon monoxide is a product of incomplete combustion. And so it's co-emitted when we burn fossil fuels with the fossil CO2. And if we can diagnose the ratio of that co-emission from these flask measurements, which we've done here, then we can use it to calculate fossil CO2 from high resolution CO measurements that we can make actually using cavity ring down spectroscopy, the same technique that Adam talked about. So for those aircraft mass balance calculations that I showed earlier, we can take those two ratios and the data that we'd already measured of the fluxes of CO and CO2, and from those we can derive fossil fuel CO2 using two different techniques. And we can find the flux in moles per second from Indianapolis. And you see that these two agree very well with each other. And I don't have time to go into the details today of two other techniques, but what I'm showing here is now comparing four techniques. The two on the right, the green ones, are the ones I just showed, the calculated flux of fossil fuel CO2 from Indianapolis using the aircraft mass balance technique and radiocarbon from flasks. The blue one is another method using measurements from towers around Indianapolis and also including radiocarbon measurements. And the red is an estimate from a bottom-up estimate of emissions based on activity data. So things like how much fuel is bought and sold and used. And you see that we've got really good agreement between all of these. These agree within 7%. Which can really give us confidence that we can measure fossil fuel CO2 emissions in a meaningful way that can be useful to people to look for changes in emissions over time. So now I'm going to go to my second example, which is called the Great Greenhouse Gas Grass-Off. And this has been quite popular with scientists and non-scientists alike. So when COVID came in 2020, we all in the atmospheric greenhouse gas community realized quite quickly that this is going to be the first time that we've ever had an experiment where emissions have actually decreased, at least in the time that we've been able to measure these. As environmental scientists, we don't get to do experiments. So when one comes along, we have to really take advantage of it. New Zealand had a very strong lockdown in 2020 and nobody was allowed to travel more than 5 kilometers from their home. And as scientists, we were not able to get permission to travel. So we came up with this idea that maybe we could get citizen scientists involved. So we managed to get both social media and the national media here in New Zealand on board and got a lot of advertising out there. And we got people to collect grass samples. Now, key here is that when plants photosynthesize, they take CO2 out of the air and they use it to grow their leaves. And they keep the radiocarbon content that was in the atmospheric CO2, that gets retained in the plant material. So if you know the time when that plant material grew, then you can infer what the radiocarbon content was in the atmosphere at that location, and therefore what the fossil fuel CO2 content was in the atmosphere at that location. And grass is a really ideal thing to use for this because it grows very quickly. You can go out and you can cut it and you can go back to the same place next week and cut it again. And so you can get weekly average samples. And so that's what we asked people to do. And we got 400 people around New Zealand participated. Not all of them sent them back, about 110 did. And out of all those samples, we were able to get 17 usable sites. And here's what the data looks like. I've skipped over the measurement of radiocarbon and gone straight to fossil fuel CO2 calculated from the radiocarbon in the grass. And what's shown here is in 2020, the measurements of weekly samples of the fossil fuel CO2 content in grass samples. And this is 2 sites in central Wellington. In New Zealand, the lockdown, level 4 was a very strong lockdown where nobody was allowed to travel. And then gradually, there was more travel allowed through to level 1, which was back to normal when we eliminated COVID in New Zealand in June of 2020. And you see this big change in fossil CO2 at these sites through this time, and that's about a 75% change in emissions. These sites in the middle of roads in central Wellington are really just giving us information about the local traffic changes. And so this suggests a 75% change in emissions from traffic in these locations during the height of the lockdown versus the normal time period. We did this at a bunch of different sites. Here's 3 more sites around Wellington, seeing a very similar story of a similar change in emissions. Here's 2 sites in Auckland, which is the largest city in New Zealand, and these are both in very central Auckland. And we see the same pattern here, but the drop in emissions is much lower, particularly in the top one, where it's only about a 30% drop in emissions. And this puzzled us at first until we realized that in this location, a lot of the traffic is buses, and the buses continued to run even during the height of the lockdown to get essential workers around the city. And so the change in emissions in this location was much smaller than elsewhere. So we put all of these together. And here I'm showing our 17 sites across New Zealand and the decrease in fossil fuel CO2 during the level 4 lockdown relative to level 1 when things were back to normal. And we see this average 75% decrease in emissions during level 4, but quite a lot of variability from site to site, which tells us a lot about specific traffic in those particular areas. And this really suggests that not only is this a way to track the change in emissions during COVID, but that as our vehicle fleets in New Zealand and around the world get more efficient, that we can actually use this methodology to look at those changes in efficiency and reductions in fossil CO2 over time. So that's all I have to say. Just to conclude, Radiocarbon provides this amazing tool to quantitatively evaluate fossil fuel CO2 emissions. I showed you from the Influx project that we can put together these methods and we can really understand fossil fuel CO2 emissions at a city scale. And the roadside radiocarbon measurements that we did during lockdown, we're really able to see what's happening with changes in traffic at that scale. And I didn't get to talk about today, but I'd be happy to take questions about how radiocarbon can provide insights into how the Southern Ocean exchanges carbon as well. Thank you very much.
I thank you first for your invitation to talk to this webinar. My presentation will focus on the use of radiocarbon for dating in archaeology and cultural heritage, what my laboratory particularly developed in the recent years. I will, oh, sorry. Better. I will start with generalities on radiocarbon dating and will then develop a few original applications. Radiocarbon, or carbon-14, is one of the 3 isotopes of carbon. Carbon-12 and carbon-13 are stable atoms, and carbon-14, with its excess of neutrons, is radioactive. At the contrary of C12 and C13, which are on Earth from the beginning, C14 is a cosmogenic atom produced in the upper atmosphere, mainly from the collision between neutrons and nitrogen atoms. It is quickly oxidized in CO2 and redistributed in the lower atmosphere, terrestrial waters and oceans. It comes into the carbon cycle via the photosynthesis for plants and then passes through the food chain. It dissolves in the continental and oceanic waters, so one can find it in aquatic plants and animals. The equilibrium between production and decay of carbon-14 leads to a natural C14 activity of the atmosphere and waters. All along their lives, living things exchange carbon-14 with their environment and present the same carbon-14 activity. When they die, their radiocarbon content starts decreasing with time, and half of the content decays each 5,730 years. It is the American scientist Willard Frank Libby who first imagines the possibility to use carbon-14 for dating. In 1949, he published the first radiocarbon dates on Egyptian objects, and he obtained the Nobel Prize of Chemistry in 1960. A fabulous chronometer for the past 55,000 years that covered the prehistory and history of humans was born. The use of this chronometer is governed by the decay equation of C14. The radiocarbon age of sample to be dated depends on the half-life of C14, determined at 5,730 years. It depends on the C14 content in the original sample N0, that is the C14 content at the moment of its death, and it depends on the residual C14 content M, that is the C14 content left in the sample after time t. The radiocarbon age is given in BP, before present, with 1950 chosen as the beginning of the C14 chronometer. The residual C14 content N is measured by the laboratory by two ways. First, count the beta emissions of the sample, first instruments developed for radiocarbon measurement, which can be quite long, depending on the quantity of carbon available and the precision expected, typically 3 days for 0.5 to 3 grams of carbons. Since the 80s, beta counting was progressively replaced by accelerator mass spectrometry that allowed to reduce drastically the quantity of carbon and in consequence, the quantity of sample required. Typically, in an AMS, 3 days are necessary to measure 100 of sample. The original content N0 is estimated and assumed to be constant with time for the calculation of the radiocarbon date, but it has fluctuated, and the construction of calibration curves is necessary to convert the C14 ages in intervals of calendar dates. Now, what kinds of material suitable for radiocarbon dating? Among all these objects, many contain carbon from a living origin, the minimal condition for radiocarbon dating: wood, bones, fabric, paper, seeds. But others do not present this condition. The Greek sculpture made of marble that is mineral calcium carbonate contains carbon, but of geologic origin, so infinitely old. The plastic bottles, the plastic bottles contain a lot of carbon, but this carbon originates from petroleum, a product considerably older than 50,000 years. And finally, between these two rock paintings, one comes from Lascaux Cave on the left, where the black color of the drawing is obtained from manganese containing pigment, while the other from the Chauvet Cave is realized with charcoal, so it can be dated and was dated. If most of the samples shown in this picture are usual samples for radiocarbon dating, 2 of them have been recently discovered or rediscovered as being of great interest for radiocarbon dating, as long as a specific protocol of preparation is used. I chose to present you these exotic materials on which my laboratory has extensively worked in recent years. I mean iron and lead white. The basic idea for dating ferrous alloys by radiocarbon is that the carbon contained in the steely zones of the ancient metal comes from the charcoal used during ore smelting. In fact, during the production of iron ore, the wood charcoal used to heat the furnace produces CO and CO2 that reduce the iron oxides and diffuse progressively into the resulting metallic matrix to form iron carbides. In the direct process, which is the first process used to produce iron, and which has been used until the 15th century, the temperature of the furnace remains under the melting point of iron. So this solid state process results in a highly heterogeneous material with a low and variable carbon content. Thanks to the presence of carbon from living matter, wood charcoal, the iron alloys from these periods are suitable for radiocarbon dating. The C14 dating will give approximately the period of production of the metal. Nevertheless, iron objects are complex samples. The heterogeneous repartition of carbon on one side and the history of the object itself on the other side must be characterized as much as possible to ensure the reliability of the radiocarbon dating. Detailed metallographic investigation of the matrix and chemical analysis of slag inclusions guide the sampling for radiocarbon. For metallographic investigation, the sample is cut, polished, and the cross-section is submitted to acid etching to reveal the microstructure and the carbon distribution. Welding lines are also visible at this tape and can indicate the presence of different iron blooms and the possibility of recycled metal. Slag inclusion found within archaeological iron artifacts produced with the direct process are remains of the unreduced or entrapped into the metallic matrix. The chemical analysis of slag inclusions provides pertinent information about the manufacturing of the object and can highlight the presence of several iron blooms. In some cases, the chemical analysis can also reveal an excess of calcium due to the addition of mineral carbonates during the reduction, a potential source of contamination. The sampling for C14 measurement with accelerator mass spectrometry is done using coated TN coated drills of 1 to 3 millimeter diameter in the highest carburized zone determined by metallographic analysis, and a few hundred milligrams are necessary to obtain up to 1 milligram of carbon. Combustion of this particle is realized with copper oxide in excess in quartz sealed tube at 850 degrees. Once the CO2 is extracted, the following steps are the same as for all the samples submitted to radiocarbon. The CO2 gas is transformed into carbon graphite in the presence of dihydrogen on iron powder. It is then pressed in target and the amount of C14 in the sample is measured with an accelerator mass spectrometer. The C14 content, corrected with standard and blank measurements, gives a radiocarbon age that is converted into a calendar date via the calibration curve. I illustrate my point with the case of the iron armature used in a medieval building, the Cathedral of Beauvais. Beauvais Cathedral is not only the highest building in Gothic architecture, 46 meters, but it has also a chaotic history. Construction began in 1225, and the core is finished probably in 1272. But the middle vault of the core partially collapsed in 1284. The most spectacular iron structure in the cathedral consists in layers of tie rods that reinforce the buttresses. The establishment of these tie rods was attributed to the 17th and 18th century, since graffiti from this period have been found on some buttresses. But we do not know if this iron was already employed during the construction of the building in the 13th century. 5 specimens were collected from the tie rod of the northern buttresses, 2 radial and 3 peripheral tie rods. 1 specimen was sampled from the chain above the vault in the main attic. They were dated following the protocol described above. The dates are presented in the table at the left and the calibrated ranges in the figure of the right. The results form three distinct chronological groups. The chain and the peripheral tie rod are compatible with the dendrochronological date established on the main roof, suggesting that all these armatures are pre-collapse. This confirms the presence of iron since the construction of the cathedral. The two radial tie rods constitute the second group of dates. They could have been placed after the collapse in 1284 to reinforce the structure after the rebuild. The two last tie rods give younger results and could correspond to one or several restoration campaigns in the 18th or 19th centuries. Our measurements definitely confirm that iron armature were viewed as ally of the stone from the earliest beginning of the building yard and even the design phase. I move on another material, lead white. Lead white is mainly composed of a mixture of two lead carbonates, cerussite and hydrocerussite. Both exist in nature and are mainly extracted from galena ores. They are also synthesized since the Greek period. One of the oldest recipes that have come down to us was written by Theophrastus in 400 BC. These synthesized lead carbonates were used in cosmetics until the 18th century and in paintings from the antiquity to the very beginning of the 20th century. It is then called lead white. There are several qualities of lead white: the superior quality made of pure lead white, and inferior qualities where lead white is mixed with calcium carbonates called Meudon white. Lead white is made as follows. Thin slides of metallic lead are placed in clay jars over vinegar. The whole vessel is covered with horse manure. The vinegar vapors will corrode the lead, and CO2 from the fermentation of horse manure will gradually be incorporated during the synthesis process to form out two compounds of interest, cerussite and hydrocerussite. Since it has been demonstrated that CO2 of organic origin is incorporating during its synthesis process, it can be assumed that this pigment can be dated by the radiocarbon method. The information that would be available is the date of manufacture of the pigment. And now, how to extract carbon from lead carbonate. In an ideal case where lead white is cured, two extraction method can be chosen: an acid hydrolysis or thermal decomposition. Generally, the extraction of carbon present in carbonate is done by acid hydrolysis. However, in concrete cases, as described in the historical documents, it is rare to find pure lead white. It is often mixed with calcium carbonates that do not contain C14. Acid hydrolysis will not distinguish the two sources of carbon. We choose the thermal decomposition at 400 degrees because at this temperature, we decompose all the CO2 present in the lead carbonate with a very good yield, and we are free of possible contamination from other forms of carbonate, and in particular from calcium carbonate, which remains stable at 400 degrees. The sample is heated on a vacuum CO2 collection line at 400 degrees to extract the CO2 from the lead white. And the rest of the preparation is the same that I showed you before. My first example is taken from a Greek material. It was selected in the cosmetic collection of the Louvre Museum. It is a pale powder found in an Eretria tomb in Greece. The tomb is dated from 330 BC to 266 BC. The powder is essentially composed of cerussite. This dating is of great interest to demonstrate if the powder is of natural or artificial origin in a period, the 4th century BC, where Greeks start to elaborate the first recipes of cosmetics. We can compare our results to the radiocarbon dates obtained from almond seed, also found in the grave and dated between 360 and 196 BC. It can be seen that the radiocarbon date obtained on this Greek cosmetic is in agreement with the two dates obtained for the almond seed. It demonstrates that the cosmetic is a synthetic product elaborated from atmospheric CO2. Another example is the painting from the Château de Germolles in Burgundy. The wall paintings of Château de Germolles represent a courtly set built of M and P initials intermingled with thistles. Philip the Bold, Duke of Burgundy, acquired the castle in 1380, then offered it to his wife, Margaret of Bavaria. She intended to convert this fortress into a princely palace and asked Jean de Beaumetz, the official painter of the Duke of Burgundy's court, to take in charge the castle wall decorations. Thanks to the accounting notes, we know that this work was performed between 1388 and 1390. An unrestored zone was very interesting because it contained pure original lead white. We took 4 samples from the initial M. The samples were prepared according to the protocol described above. 20 to 27 milligrams of powder could be sampled, and we collected between 0.3 to 0.5 milligrams of carbon. After calibration, 3 of the 4 samples give results consistent with the historical date obtained from the counting notes. We could hope that the weighted average of these 3 dates in blue would reduce the interval, but the 14th century corresponds to a plateau of the calibration curve that limits drastically the precision of the calendar dates. The interval obtained for one of the samples is younger than expected. It is probably due to a subsequent paint retouching or a very small modern contamination of the sample. The results are in good agreement with the period expected, showing the efficiency of the protocol proposed for the preparation of lead white. And I thank you for your attention.